Hello everyone. We have calculated the equilibrium velocity of a planetesimal. The cross-section for collision is dependent on the velocity of a planetesimal. Now we are ready to calculate the growth of a planetesimal. We are going to consider the growth rate of a target planetesimal, blue planetesimal. Mass of the planetesimal is a capital M. We expect that all the planetesimals inside of this cylinder can collide with the target planetesimal. The area of the cylinder is expressed as sigma, cross-section for collisions. And the height of the cylinder is expressed as v dt. V is the velocity of planetesimals. Number of planetesimals inside of the cylinders can be calculated. The volume is expressed as sigma v dt. Volume times the number density give us the total number of planetesimals hitting to the target planetesimal. So increase in mass of the target planetesimal, d capital M, is expressed mass times the number of planetesimals. So mn sigma v dt. If you divide it by the dt in the both sides, dm dt equal mn sigma v. This is the growth rate of a target planetesimal. We find the growth rate of a planetesimal. Planetesimals make nearly the circular motions with a small eccentricity and a small inclination. So random velocities, as I explained, can be expressed with E times the Keplerian velocity of the v sub k or 2i v sub k. Surface density of the planetesimal can be expressed sigma sub m equal mn times the 2ia. 2ia corresponds to the thickness of a disk. Then this can be expressed v over v sub k. And the v sub k equal a omegas. Then surface density of the sigma sub m can be expressed mn v over omegas. Omega is the angular velocities. Then growth rate can be expressed with the surface density of the sigma m. Sigma m, sigma omegas. Then you can substitute cross-section for collisions. So this part is a cross-section for the collision of sigmas in the case of the two-body problems. Then we just only consider the gravitational focusing effect becomes significant. So we just only take a gravitational focusing effect. Then R square is proportional to m to the 2 over 3. This R is proportional to the m to the 1 over 3. This is proportional to the m to the 4 over 3 because of the m appears here. b to the minus 2. So we consider energy equipartition is maintained between the planetesimals. Then and the log m. M is the mass of the planetesimal. If you consider only the small planetesimal following this month, the larger planetesimal v is proportional to m to the minus 1 over 2. So you can use the energy equipartitions between the planetesimal is satisfied. Then you can substitute this expression is here. Then growth rate is proportional to the m to the 7 over 3. For simplifications, we assume the planetesimal population is composed of a number of small planetesimals with mass lowercase of the m, and a single planetesimal with mass of the capital M. We will compare the growth of two planetesimals. Take a ratio of the capital M over lowercase of the m and the derivatives. So these derivatives can be easily calculated. Find that the common factor of the m over m is a 1 over m dm dt minus 1 over m dm dt. We have already discovered dm dt is a growth rate of the planetesimal is proportional to m to the 7 over 3. Then 1 over m dm dt is proportional to the m to the 4 over 3. So this part is m to the 4 over 3. This part lowercase of the m 4 over 3. Now capital M is larger than the lowercase of the m. So this is larger than 0. So this means the ratio of the m over m increases with times. So once the one single object of the M is larger than the other, this planetesimal quickly grows to the large. A large planetesimal grows much faster than small planetesimal and becomes a protoplanet. So this becomes a protoplanet. This is called the runaway growth of a planetesimals. After the runaway growth mode of planetesimal move to the next stage of the oligarchic growth. Once a protoplanet becomes massive, about 100 times more massive than a planetesimal, it enhances the velocity of a neighbor planetesimals. The velocity of a planetesimal is approximated by the escape velocity of a protoplanet. V is nearly equal to the escape velocity of a protoplanet squared 2gm over r. R is proportional to m to the 1 over 3. So escape velocity is proportional to m to the 1 over 3. So we derived this expression. This is m to the 2 over 3. So this becomes constant value with respect to the m. Then m dependence is appeared r squared. So growth rate is proportional to the m to the 2 over 3. Now we consider two protoplanets with the masses of the m sub 1 and m sub 2. Right now, m sub 1 is a little bit larger than m sub 2. Then consider the ratio of the m sub 1 and m sub 2. d dt m sub 1 over m sub 2 is equal to the m sub 1 over m sub 2. 1 over m sub 1 dm sub 1 dt minus 1 over m sub 2 dm sub 2 over dt. dm dt is proportional to the m to the 2 over 3. So this means 1 over m dm dt is proportional to m to the minus 1 over 3. So this part is m sub 1 minus 1 over 3. This part m sub 2 minus 1 over 3. Now we consider that m sub 1 is larger than m sub 2. So in this case, this becomes negative quantity. M sub 1 over m sub 2 take a vertical lines and the horizontal line is a t's. So this is the point of the ones. So even if you start from the larger values, this ratio is decreasing in the approach to the ones. The difference of the masses of the protoplanet is decreasing with times. The distance from the stars, central stars, formed protoplanet has a similar size, m sub 1, m sub 2, m sub 3. And we have so many planetesimal. Then we call this growth mode oligarchic growth. Protoplanet grow together with a similar growth rate. Finally, we'd like to estimate time scale for growth of a protoplanet, tau subgrowth, equal m over dm dt's. So we derive the growth rate of the dm dt's. We substitute. And then we consider gravitational focusing effect is a significant case. In the terrestrial planet regions, we consider that m is a Earth mass. Tau growth is estimated 1.1 times 10 to 8 years, so 100 million years to form the Earth-sized planet at 1 AUs. In the gas giant regions, we consider m equal 10 Earth mass. Then growth time scale is 4 billion years. A equal 5 AU from our central stars. So it takes long for a protoplanet to grow in the outer regions. A protoplanet in the outer regions need to capture gas from a disk to become a gas giant planet before gas is removed from a disk. The lifetime of a gas disk is observed to be about a few million years. So in the next chapters, I'm going to explain how to capture gas from a disk to form a gas giant planet. Okay, this is the end of this session.